this lab we're dealing with liquid crystal cells, and so a liquid crystal is a medium that is somewhere between a liquid and a crystal, and so it has a regulated structure that tends to follow a director, as you can see here, but the individual molecules can move around like in a liquid. We're dealing with a liquid crystal cell, and so a normal liquid crystal cell is a layer of liquid crystals that are smushed or sandwiched between an alignment layer, then two transparent electrodes, a layer of glass, and polarizers. The alignment layers act to twist the liquid crystal cells. When we have no voltage applied to the system, it's considered on, and light can pass through the liquid crystal cell. And when there is a voltage applied, it causes the molecules to move and change the polarization, and turning the cell off.
In this part of the lab, we use the Axometrics polarimeter with two different LCCs. We have our Thorlabs one here and our Boulder Vision one here. For the Thorlabs one, we used both of these color filters. This one is 535 nanometers, this one is 633 nanometers. We put it in here like this. And then we input for the function generator a 2000 kilohertz square wave, and we varied the voltage from 1 volt to 9 volts peak to peak at 0.2 volt increments. And we saw how that affected the output retardance, the Mueller matrix, and the orientation of our LCC measured on our program on our computer. We did it with two different color wavelengths for the Thorlabs one in order to measure its performance at both, or its performance in between comparing two different wavelengths. We only used the 633 nanometer one for the Boulder.
Using the axometric program, we could determine the Mueller matrix of our different LCCs. The Mueller matrix can tell you many different things, including the retardance, deattenuation, depolarization. The axometrics device works by having two fixed linear polarizers and then rotating two linear retarders. And by measuring the change, as these two retarders change, you can measure the Mueller matrix of the sample that's in between.
So this is the Axometrics Axolite program we use to measure all the various parameters of our LCC. We have our Mueller matrix down here. We can measure our retardance, attenuation, polarization vectors on the Poincare sphere, which you see right here. You can either run it once or you can run it continuously, and you can see we just sort of have our thing sitting there right now, so it's jumping around a little bit. And then you can save our data, which we use to process later.
When we were creating our signal for our system, we used a 2 kilohertz sine or square wave because our LCCs cannot respond to a wave of that speed, so it sort of sees it as a DC signal, but if we apply a DC signal, it can actually damage the LCC, so this is our way of sort of recreating that without damaging the LCC.
We used our liquid crystal cell to create an intensity modulator. So we have a laser coming in, and then we have a system with cross polarizers, and we put our cell in between that will retard the beam depending on the input voltage. So we changed our input voltage from peak to peak readings from 1 to 9, and that we read the output transmission, and from that we plotted that, and we were able to see how the voltage affects the transmission of the system. For the next part, we chose the maximum transmission voltage and used that, and then rotated our axis of this to see how that changed the system. Here's the data from when we did the polarimeter with the different LCCs. So with the Thorlabs with 535 nanometers, most important is the linear retardance and retardance magnitude are identical for everything we did. And the retardance orientation, it flips at this point. This illustrates the ambiguity in the system. So what we want to do is do 360 minus this part, and that corrects it and gives us this. Similar thing for when we did 633 nanometers, the orientation flips at this point, so we did 633 minus this to clean up the graph. When we used the Boulder Vision, it was much nastier data, but this is what it gave us. This is our data when we used the intensity modulator. So for the input voltage, we measured the output voltage, and it was pretty noisy at the beginning, but generally it follows this curve. And then the next part, we chose the maximum voltage right here, and kept it at that and rotated around an axis, and this is what we got. We would expect it to have this pattern all the way through, but it didn't. That's because there was a lot of noise in the detector.